Today's lesson has to do with zero exponents and negative exponents and what they mean. So one thing I'd like you to do briefly is actually take out your calculator. I'm going to pause the video while I open up mine. And I'm going to type in a few things. I'm going to type in 9 to the first power. I'm going to type in 9 to the negative first power. And I'm going to type in 9 to the 0th power. If you kind of look at what's happening here, and let's go back to the notes, we're going to talk about what these mean with power of zeros and negative powers. Let's start with the power of 0. This is a powerful one, pun sort of intended, but the power of 0. Basically, if we have 0 as a base, this is different than 0 as an exponent, but 0 as a base, we can pretty much say that that base raised to the first power is 0, that base to the second power is 0, that base to the negative 1 power, let's try this one. We're going to go 0 to the negative 1, and that one's undefined. And if you recall back, we said the only other thing that was undefined was 1 over 0. Actually, anything over 0. But this is what we consider to be undefined, and we're going to kind of learn a reason for this very soon here. If I do 0 to the negative 2, let's try that one. 0 to the negative 2. Ooh, that one says infinity. What about 0 to the negative 3? That one says undefined. 0 to the negative 4. Well, we're not going to kind of talk about the differences. I'm actually going to change this a little bit, and I'm going to call this undefined as well for our purposes. But if you're curious about what calls this one infinity, come ask me. We'll talk about it. And there is a reason. But for now, I want you to kind of look at this and sort of see some of the patterns we're doing here. These make sense to you, but this is kind of new here, a negative exponent. And you might be wondering, well, what about 0 to the 0th power? If I go 0 raised to the 0th power, ooh, that's undefined. So let's talk about what this means here. These are powers of 0 here. And if I take this 0 to the negative 1, and that's undefined, we want to give a reason for that. Well, part of the reason is this idea of the rules of negative exponents. The rules of negative exponents, I kind of simplify this to say that a negative exponent, it means nothing more than the reciprocal. Negative exponent means reciprocal. And it implies that we're talking about the reciprocal. So the rule of this is that if I have a to a negative power, that's the same thing as 1 over a to that power. Or another way to kind of carry this forward is that if I have 1 over b to a negative power, that's the same thing as b to the positive version of that power. Now there's a couple of disclaimers here. This is provided that a is not equal to 0, and this is also provided that, well, we'll kind of keep the n is not equal to 0 here, and this would be b is not equal to 0, because you simply can't have 0 in the denominator. But this does carry meaning here. So when we have a negative exponent, if I want to do a few simple examples here, if I go 7 to the negative 2, that's the same thing as 1 over 7 to the second power, which we know is 1/49. If I go 317 times 10 to the negative 5, which is a scientific notation, and some of you may have seen that. Actually, it's a version of a scientific notation, because I don't have a decimal point on the 3.17. But that's the same thing as, and I'm going to kind of treat this as drawing a fraction bar and putting this over 1. That's the same thing as 317 to the first power over 10 to the positive 5th power, which is 317 over 10,000. As a little side note, I know I can't reduce that because 10,000 is just made up of 100 and 100, which is made up of just 10s and 2s and 5s, and 317 is not divisible by 2s or 5s. Let's look at another example of this. 6 to the negative 1, x to the negative 2, z to the third power, over x to the negative 1, z to the negative 5. Well, if I look at the operation that's in between all of these, I have multiplication in between each little part here. Multiplication there, multiplication there. And so I can sort of break this apart into separate fractions. Now, we're not going to do this every time, but I want you to see this as broken apart into separate fractions. And I'm going to have 1 over x to the negative 1 and 1 over z to the negative 5. And 6 to the negative 1 over 1 is the same thing as 1 over 6 to the first power. And this is 1 over x to the second power. This is still z to the third power. This is now x to the first over 1. And this is z to the fifth over 1. And now if I bring them back together, my numerator I have x and z to the third times z to the fifth. Add and multiply with the same base, we add the exponents. That's z to the 3 plus 5. Then I have in the denominator 6 and x squared, so this is going to be x times z to the 8th power over 6x to the second power. Then if I look at these two, I can reduce that to get this. We will not spend that much time doing this, but we need one more little piece of knowledge before we move on. That's kind of how we deal with negative exponents. Let's talk about 0 as a power. We're going to list off, I want you to put powers of 2. 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, 2 to the 0, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and that's enough. Okay, 2 to the 5th is 32. 2 to the 4th is 16. 2 to the 3rd is 8. Sorry. Look at the pattern here. This is divide by 2. And if I kind of continue, 4, 2. If I divide by 2, I get 1, and then if I divide by 2 again, I get 1/2, and then 1/4, and then 1/8, and so on. My target here is this, that 2 to the 0 is equal to 1. And if we can kind of treat this, I can sort of generalize and say that when I have 0 as a power, anything to the 0 power is equal to 1, provided that that anything is not in fact 0. Because as we saw up above, I could put an arrow. I saw up above, I know that 0 to the 0 power is undefined. So, a couple of things to kind of keep in mind here. If we have 0 as a power, I know that anything to the 0 power is 1 except 0 to the 0, and that's undefined. If I kind of continue with some examples, let's see, we're at example number 4. Let's do some basic ones. We're going to go negative 5 to the 0 power. And I'm going to compare that to negative 5 quantity to the 0 power. So let's look at the first one again. If I look at where the grouping symbols are, they're kind of stuck here around the 5. I don't know why I drew those so weirdly, but there they are. They're in a different color. Negative 5 to the 0 power actually kind of implies that that 5 is going by itself, and then exponents happen first. So this means the same thing as negative 5 to the 0 power like that, which is negative 1. But this, I have the entire thing raised to the 0 power, so what that is meaning is that this whole thing is equal to 1. Really nothing I can do to simplify that or to show that. It's just that when you have a base raised to a 0 power, that's equal to 1. Sometimes in Algebra 1 I do these fun things where I actually put something like this. X squared minus yz cubed plus 5400 q to the 5th, and then I'd say that quantity cubed, and then I take that and I raise it to the 0 power. And some of my kids will fail to notice that that's a 0 power, and they'll work their way from the inside trying to do some ridiculous things. Or I'll have them substitute, but really to the 0 power that would just be equal to 1. So those are some things that you can do with the 0 power. I want to put a little sidebar here as related to the problems number 4 and number 5. Just a little reminder, if I have this, that is not always the same thing as negative x quantity squared. That this notation right here of negative x to the second power, this means the opposite of x squared, because by order of operations I'm raising to the exponent and then I'm multiplying by the invisible negative 1 that's sitting out there. So just a little reminder of that. Here's a consequence of that little sidebar I did. If I have negative 4 to the 4th power, that's the same thing as negative quantity 4 to the 4th power. 4 to the 4th power, as we're going to learn later, I can kind of treat that as 2 to the 2nd power to the 4th, but for right now it's enough to know that that's 16 times 16, because it's 4 squared squared, and that's negative 256. Want to kind of go back to this right here. I'm going to dissect this just a little bit in a way that's going to be meaningful coming down the pipeline. If I make that negative 1 times 4 to the 4th power, this right here is called a coefficient. This is called a base. And this is called an exponent. And later on it's going to be important to know the distinctions between all of those, but that should have an idea of why you end up with a negative 256 and not a positive 256. Believe you me, we will be testing you on that, and I want you to know that this ends up with this, negative 256. Let's pop down to some more examples. I'm going to go 7 to the negative 2, x to the negative 4, z to the negative 5, over 8 to the 0th power, x to the negative 3, z to the 4th. I'm going to simplify this. So the first thing that I see is I have an 8 to the 0th power, and since again this is all multiplication, I'm just going to slash this. That's equal to the number 1. It's not going to affect the final result, so we'll just leave it there. Then, instead of what I did before, we're going to play a game that I've heard too called popcorn sometimes. You have a negative exponent, you go down, and if you have a positive exponent, you stay. What I kind of do is I take this and I will read it left to right, like a book. And if I see a negative exponent, that sucker's going down. 7 squared, then I see the x to the negative 4th, becomes an x to the positive 4th. Z to the negative 5th becomes z to the positive 5. Then I look down, x to the negative 3rd pops up as x to the positive 3rd. Z to the 4th stays exactly where it is. And then we play the canceling game. I'm going to draw my fraction bar again. My x cubed is going to cancel with that, leaving me an x to the 1st power. So I'm just going to put a 1 on top. 7 squared is 49, x to the 1st, and my z to the 5th and z to the 4th become z to the, well, we add to get 9. Erase the 1, I don't need that. This is what my final will look like. Okay, new directions. Let's express without a fraction. So I've got number 9 here. 4 over 1 million. And I don't want it to be a fraction. So instead of 4 over 1 million, I'm going to change that into 4 over 10 to the 6th. Ooh. Notice how I didn't reduce that. You could, but this is kind of a little bit more of a simple way to do it. And that's going to be the same thing as 4 times 10 to the negative 6th. And that form is what we call scientific notation. Also something you'll be seeing more of a little bit later. We're not going to do it here, but I do want you to know that that form is true scientific notation. Number 10. 2a over t cubed b. This is a little bit easier. The 2a is going to stay exactly where it is, but the t cubed and b, I'm going to put those in alphabetical order, and we'll start with the b. It's b to the negative 1, t to the negative 3. Number 11, I'm going to go negative 1 over 4 to the negative 1 to the negative 1. And let's kind of reset the directions here. Sorry for the space gap. We're going to call these more simplifies. These are some numbers that I like to mess with. Sometimes I try to mess you guys up. If we're going to simplify this, I'm going to work my way from the inside out, starting with this and looking at this. Everything else is going to stay exactly the same. Actually, I'm going to work vertically. So I'm going to go negative, and I'm going to keep this sort of locked in its own set of parentheses. 1 over 4 to the negative 1 is 4, and I'm going to have that to the negative 1. Then I'm going to cut the inside parentheses out and just make this negative 4 to the negative 1. And then the negative 1 exponent means 1 over. So that's 1 over negative 4, which we typically write as negative 1/4 a little bit more casually. So let's move that up. Let's try another one. Negative 3 to the negative 3rd. This one is clearly one I'm trying to mess with you guys on because of all the 3's. So again, I'm going to look inside, nothing to do there. Then I'm going to go exponent, so negative, and I have 1 over a negative 3 cubed. Well, negative 3 cubed is the same thing as negative 27, and that becomes positive 1/27. Let's go to number 13. A to the negative 2 plus b to the negative 2 to the negative 2. I want you to know on this I am absolutely deliberately trying to mess you guys up. And what I'm trying to do here is make you carry that over and try to distribute that, and you cannot. You cannot distribute an exponent across plus and minus for the simple reason that you can't kill puppies. X plus y quantity squared is not equal to x squared plus y squared, and you know this. It is in fact equal to x squared plus 2xy plus y squared. And if you distribute exponents, you kind of miss this missing middle term here. So the best I can do is actually just kind of rewrite this without exponents. Make this 1 over a squared plus 1 over b squared to the negative 2, which would then be 1 over a squared plus 1 over b squared squared. And that is a little bit of a to be continued, because we will learn how to add those, but not right now. Still, I wanted you to see this example that they're not the same. In fact, what I want you to do for the last example is prove that x plus y to the negative 3rd is not equal to x to the negative 3 plus y to the negative 3. And you're going to do proof by counterexample. Just pick any two numbers for x and y that are not trivial. You don't want to pick ones like 0 and 0. So let's go x equals 1, y equals 2, something simple. And I'm going to substitute those. On the left side it becomes 1 plus 2 to the negative 3rd. And on the right side it becomes, let's see, that'd be 1 to the negative 3 plus 2 to the negative 3. And let's go back to the left. That's 3 to the negative 3rd, 1 over 3 cubed, or 1/27. And on the right side, that is 1 over 1 cubed plus 1 over 2 cubed, or 1 plus 1/8, or 9/8. And clearly you can see that those are not equal. So that is a proof. If you guys want to say something at the end that's a little clever, you can put a little box, which means this is done. Or you can put a QED, which means quod erat demonstratum, thus it is demonstrated. So that's it. Good luck. You've got a page 218 and a yellow worksheet, but I'll let you find that yourself.